kind of a tag team effort, and there's a number of people involved in this kind of new initiative, and I'll talk a little bit about the history of the initiative. All the people here, plus additional people I haven't mentioned, have helped get this thing going. And I'll give some background about how it all came together. This idea to essentially use the Earth GCM to model other planets and even other worlds outside the solar system. So I said this is a new astrobiology group, and astrobiology, as you can see from this Wikipedia definition, is more or less it encompasses anything that you wanted to in a sense. But we're really going to focus on this search for habitable environments in our solar system over time and habitable planets outside. So that's the focus of the group as it stands. And what do we mean explicitly like that? Well, about that, well, the first is NASA's always harping on to follow the water, find the water, right? So what do we mean by that? So
actually, back up one slide so I can take a picture.
You want a picture? I put the slides online.
Yeah. No, I've got a picture of everybody.
This is my closest collaborator.
Okay.
Nancy, I can give you a copy of the slides.
You never publish anything that you have to do.
That's true. She can publish these photos. I hadn't thought about that.
We're in the starting phase of a new era.
This is going to be a rough crowd. Okay, so a major goal in the astronomical community as it stands is to find planets around nearby stars that can support liquid water on their surfaces. And future projects, I should have said plural there, will target such candidate habitable worlds for mission spectroscopy and imaging if NASA ever gets the money to build the missions that can do that kind of stuff from space, which is where a lot of it takes place. And our 3D planetary GCM, which we call Rocky 3D, or you'll see the word graph, that's a previous incarnation of the name. I won't go into the acronym discussion, but anyway, we'll be able to verify this ability of a given planet to host liquid water and distribution over the surface of that planet. That's the motivation for this. The origins of the group come from earlier attempts to get things jump-started in this community. And by the community, I mean in New York City. There were two previous NASA Astrobiology Institute proposals that were submitted with American Museum of Natural History, Columbia University, Lamont, and GISS. Those efforts were led by Kayla and Kristen. Kayla was the unfortunate gatekeeper for those efforts. And Kristen Manu was involved when he was at Columbia, and several people here have been at the museum, and some people at Lamont. So that's kind of how the community originally got started, and many people that are on this effort now were involved in those efforts back then. Of course, I think that everybody in astronomy, and maybe even outside of astronomy, know about the tremendous changes that have gone on in the astronomical world with respect to this finding of extrasolar planets around stars. That has completely changed the field of astronomy in the last 20 years. If you had asked somebody 30 years ago what would be the next big thing in astronomy, they probably would have said, oh, we're going to discover dark matter or dark energy and all this kind of stuff. No, they would be wrong. It was finding planets around nearby stars. So this is exerting a lot of pressure on the field. And you see that in the National Academy of Sciences decadal review, which we talked a little bit about yesterday for astrophysics and the push for this on that side of the house. And then, of course, we have a lot of in-house expertise on planetary systems. I mean, Cassini, results from Titan, which Tony's involved with, and Michael Allison and his group's long-term involvement with Mars. In fact, Michael had one of the first Mars GCMs that was built from an earlier version of our GCM called Model 2. So we have these things kind of going for us in a sense, along with these other influences to kind of push us into this. And of course, there's more funding avenues available nowadays too.
You're forgetting Venus. No.
Yeah, I can get to Venus. But Venus is a little tricky for us.
I mean the
we have
heritage.
Venus expertise from the past.
Yes.
But Venus doesn't have a lot of liquid water on the surface.
Okay.
Well, it had passed.
It's not habitable.
We're going to
No,
get there. So our funding for this group started out really in 2012, fiscal year 2012, with something called a Science Innovation Fund. That was some pilot money we got from Goddard for a small group of us, Tony, Nancy, myself, and a couple people at
people at Goddard actually pushed it.
They pushed it, yeah, they got it.
Yeah.
But that got us jump-started to
Yeah.
give us a few about an FTE to split amongst us to kind of get some development going. And then this year we got some science task group funding also from Goddard to keep doing this. This is a much bigger group, and that also was led at Goddard, but we're piggybacking on that more or less this year to help us write the NASA
Well, I wouldn't say
Astrobiology
it's led.
Institute.
There were three different groups.
Yeah, that
And
were.
then the headquarters, or the management just wanted to see one proposal from
Yeah.
all of us. So we banded together, so they're basically three PIs to this SDG or whatever.
Yeah.
it's called.
That's right, one of the things is doing that.
And we're the only ones who are getting it done.
I think that that's true, but a lot of our effort, a lot of the funding for this is going to help us write the proposal for the National Astrobiology Institute. And those proposals are a 5-year program with quite a lot of money compared to the normal ROSES grant. In the meantime, we've also gotten 2 proposals funded, one by Tony through the Planetary Atmospheres program to look at Titan Earth and early Earth comparisons with this modified GCM we've been working on, and then Linda also just recently got word that her exobiology proposal was funded to do reconstructions of snowball Earth. So we've had some really good luck. And then, like I said, the goal is to get one of these NAIs, which would be a 5-year program to look at rocky planet habitability and with insights from solar system climate dynamics through time, which I'll touch a little bit more on as we go through. So what is the work that has been done to date? We'll go into more specifics about these, but the first is the work that Linda and Mark and Jeff have been doing for several years here on paleo Earth and snowball Earth glaciation. Recently, Nancy managed to get an Mstar spectrum in the model to see how that affects Earth climate if you use an Mstar, which we'll talk a little bit about what we mean by Mstar as time, when time comes along. But I won't go into what the mnemonic means, but the Mstar sits down here at the faintest end of the category of stars. Our star is a G star, and O stars are the brightest stars that are born in the universe.
LT aren't stars, LT aren't stars.
I'm not going into the specifics of those small subcategories. It'll take too long.
How long lived in the Oak?
O stars live 100 million years, something like that or less. All these things blow up into supernovae essentially. They don't live very long. You're not going to find many planets around them, or if they are, they'll be blown to smithereens.
Very, very few of them.
Yeah. Yeah, exactly. Initial mass function is, as we'll see today's colloquium at Columbia, we'll talk about the initial mass function of stars actually at 15. And then we've gotten quite a lot of work done on a modern day Mars. And the idea is to eventually extend that to a paleo Mars environment where we might have water on the surface of Mars, which as you all know, we can't have in Mars' current atmospheric conditions. And then some experiments looking at the inner edge of the habitable zone, assuming we have time to get there. So I don't expect you to read this, but this is a Google Doc that we are updating within the group for the different kinds of model stuff that we're probing at the moment. So this is a column that talks about what we call our like Mars model. It's not Mars, it's like Mars. And different things that we have put in the model or different things we've changed for those specific things. Here's the inner edge of the habitable zone changes, or things we need to know about the model. Neoprotozoic, like Phaerozoic, and then Nancy's Mstar stuff. So things about the radius, the gravitational strength of the planet, and the rotation rates, all that kind of stuff is put in here, and what the resolution of those particular models are. Most of the model development so far has been in the 4x5 20-layer model, just because it's fast. You can get a few hundred years in a couple days simulation. Of course, with some various kinds of footnotes. But I'm not going to go into details of this, but some of those details will come out as we move forward. So I'm going to turn it over to Linda, and Linda's going to talk about her work with the paleo Earth stuff with Mark and Jeff. So.
Okay, just to give some general context for the things that we are hoping to do as part of the NAI, should we be funded, we'll be looking, Mark and I will be looking specifically at 5 time slices, but there is other work that is planned for Earth at other points in its history. So the diagram on the left here is sort of a summary to help set the context for the various time slices that the entire group is going to be looking at across different planets. And Earth here in the middle. So the earliest Earth, the Hadean Eon and Archean Eon, are going to be handled mostly by folks at Goddard, Sean Goldman, and Marley is at Ames, right? Yes. And so this is going to be involve a number of sensitivity experiments that are looking at a very different atmospheric composition compared to modern. What Mark and I are going to focus on is this latter part of Earth history down here. So there are a couple of snowflakes here that represent some of the more extreme glaciations that we know of from Earth history. These are the snowball Earth scenarios. There is a hypothesis floating around that suggests that these snowball Earth scenarios involved a complete freezing over of the surface ocean. There's a lot of controversy surrounding that particular idea, so it was one of the things that we wanted to revisit with our new and improved version of the model. Mark and I had previously done some of this work with Jeff, actually dating back to my grad student days in the last century, but with Model 2. And so this is an update of that work. So this is this time period that we were calling Neoproterozoic also. It's basically from 1 billion years ago to 541 million years ago, and various events happening in this time. Ediacaran falls at the end of that period, and that's the time in Earth history when we find the first appearance of multicellular organism fossils that are visible to the naked eye. So we've gone beyond the microscopic phase. And that appearance of those organisms is thought to be related to an oxygenation of the surface ocean to a significant level for the first time. And then this latter part here is the Phanerozoic Eon. So there are 3 time slices that we're going to look at in here. And just to do a little more summary here. So the first of these, the oldest one, is called the Late Ordovician period. This is a time in Earth history when most of the continents are oriented in the southern hemisphere. So the northern hemisphere is largely blank. And we don't have vascular plants colonizing the land surface yet. So this is still a very primitive landscape surface. It's a time, we think, of relatively high CO2. Exactly how much is unclear. And it's also
plenty of oxygen.
Yes. So we're basically now at this point in time for the Phanerozoic, we are basically at present atmospheric levels, with some modifications of a few percent. The next time slice is going to be this Triassic-Jurassic boundary interval. So this is the time of the supercontinent Pangaea. Folks have probably heard that name before. That's a big continental landmass that was basically saddling the equator, extending north and south into the mid-latitudes. And that particular time period tends to be a mixture of extensive deserts, dune seas, but also lots of vegetation, modern style vegetation, in sort of a mosaic, as it were. And then the last period here is the Cretaceous. So this is a time in Earth history when CO2 is thought to be high. There's no ice on land that we know of, or very small amounts of ice. So continents are flooded. We have lots of vegetation and swamps extending into high latitudes. Lots of shallow continental seas. And this is a period that might be considered super habitable, so even more favorable to life than our modern setting. So these are the 5 time slices that we want to look at. And just to talk about a little bit of what's done already. So the process of doing these time slices is kind of labor intensive because we need a continental reconstruction for each time period, and then we have to assemble vegetation data sets as appropriate and so on. But we were starting here with one of the snowball Earth intervals. This time slice is from about 715 million years ago, and it's called the Certian glaciation. It's a little hard to see here, but the continents are, again, mostly grouped together on either side of the equator. The north and south poles are clear of land. And what we're looking at here is a surface air temperature anomaly for after about 450 years of simulation compared to the start of the run. So what we're seeing here is extensive cooling in the polar regions, with the greatest cooling closest to the continental edges. And you can see that in this north polar projection. These are the continents here. And we have the greatest area of cooling here, and this is just sort of downwind. Thank you. This area is just sort of downwind from there. And we're looking at pretty significant cooling as a whole. So this is just with modern orbit. Yeah, so let me explain. This is with the AR5 version of the model, but with Max's correction to the Jeff McWilliams scheme. So it's not AR5 prime, it's just a little bit beyond AR5.
Can I ask about the distribution of continents and oceans in this model, and you know, the average topography of land versus ocean? How deep were the oceans?
So
were they shallower? Were they more extensive? Was the land area comparable or much smaller than that of modern continents?
So when you do reconstructions of the continents, to some extent you are looking at a minimum possible surface area. Because with plate tectonics and bits and pieces moving around over time, you have some destruction of continental crust. So we may be missing pieces that once existed. So this reconstruction is based on some work that was done using paleomagnetics to constrain the latitudes of various continental pieces. So just for example, this piece here is North America tilted on its right side. This piece here is the East Antarctica. This is basically Scandinavia. That's Greenland there. These are two pieces of South America, and so on. So the area is basically a minimum area, but we've accounted for the largest pieces. So we don't expect there to be a huge discrepancy between modern land area distribution and what's back then. For this set of runs, because this was the first time we ever tried this with Model E, and we were concerned about getting the ocean functioning properly, because that's the biggest bear, as Jeff can tell folks. We have not yet introduced any reconstruction of land topography, so this is just a uniform topography of 50 meters at this point in time. The next iteration of this will have reconstructed mountain ranges and so on, based on geologic data. And as far as the oceans are concerned, because we have no proxies for what surface temperature might have been like or salinity, we start with modern and we let the model go from there and respond to the forces.
But what about the average depth?
So it's just 5,000 meters. We did a bathtub ocean here, because again, there's been only one attempt that I know of to actually have any seafloor relief in a model thus far, because we don't know. We have no knowledge of the seafloor topography before 180 million years.
But even the depth, I mean, it's very arbitrary to say that it's 5,000 meters. I mean, how that may change drastically.
It's not that likely at this late stage in Earth history. Whatever water was on the surface is what we have, and we're just changing the shape of the basin.
And these the origin of the water in the ocean.
That's early in Earth history. That's not really a consideration or a concern for us at this point.
So they were actually.
So when you do like paleo,
Mhm.
do you account for the gravity changes? I think like, I don't know exactly how far that, I mean, like gravity changes as the planet ages. So I don't know if it's
Well, what do you
Only
mean
because of the
gravity
redistribution of mass on the
I
planet?
think
The mass of the planet is fixed, so the gravity is the same. The only difference is that it spins faster or slower. You might get some small amount from that, but that's trivial compared to the mass of the planet as a whole. The mass of the planet does not change over time.
Which was my question.
This is
day
just-
length you were seeing.
Yeah, exactly.
This is modern day length here. That's something that we want to change definitely because
About a million years ago, what was the difference?
at this time, the length of day was about 21.9 hours. At least reconstructed from tidal rhythmite deposits. That's the data that's been.
Are you talking about the distribution of mass, so the very local gravitational field shifts? I mean, those are minute. Right?
Well, I think I was thinking, I don't know much about planet, but we see that like when the planet gets getting smaller and smaller, like a black hole, for example, they have a
Planets
very
don't-
strong,
They
but
don't
totally
change
different.
mass.
Okay. And then I found the Wikipedia. They actually talk about the gravity changes. As the planet aged, gravity getting stronger. So I don't know. I thought that maybe
That
it's
doesn't
something-
sound-
Maybe
No,
one of
that-
those
that-
things that you shouldn't
Okay.
believe in.
What that sounds like to me is an idea that some folks, and this is not a scientific idea, this is lay people interested in trying to come up with some concepts of their own of how you could get animals as large as some of the largest dinosaurs active on land. And then they say, well, the gravity had to be less because otherwise they couldn't. So I think that sounds like that's where it comes. So that would not be an issue here. I should say also for this time period, we've turned down the sun's luminosity by about 6%, although we have not modified the spectra for this time period. It's just a total reduction at all wavelengths.
Did you modify the rotation rate?
We did not modify the rotation rate in here. For this,
But you just said it was 21 days.
well, that's what we will like to change it to, but this, we have not done that yet.
Oh, I see.
So what's the insulation then for this? Where you put in?
94%.
94%.
Yeah.
What was the trigger for the glaciations?
We don't know. That is a subject of a lot of discussion and controversy, and with some luck, we'll be able to explore that in a series of time slice experiments and looking at different forcing factors. This, by the way, in addition to the reduced solar, we have CO2 set at 40 ppm.
And then in terms of the linkage, I mean, the orbits and the inclinations, all those things are modern day.
They are left at modern. Now, some of the stuff that Caleb is doing may give us an idea for alternatives that we can try out.
We'll touch on that.
I mean, the thing that will shift is the lunar position. Right, that will alter the light-convection cycles, but we don't quite know how yet.
But we can get to that later.
So why is carbon dioxide so low? Just because it's assumed to be all like absorbed in the ocean because of the cold temperature?
It's mostly an effort to try to see how we could trigger glaciation. So the original dispute over these glaciations was the extent of ice sheet cover on land. That's what it was like when I got into this discussion as a grad student in the 90s. And that argument had been going on for a couple of decades at that point. What it evolved into by the end of the 90s was a lack of concern about what was going on land versus getting sea ice cover to be as extensive as possible. And I won't go into all the details of that right now, but that's the Harvard folks, Paul Hoffman and Dan Schrag, and their snow earth hypothesis from 1998 2001. And more importantly for us, a lot of the climate modeling efforts that have been done over the last 15 years have focused on trying to get total sea ice cover. Because I think from the modeling perspective, that just sounds like a really cool problem. So that's the way it's been tackled. From a geologist perspective, that view is a little bit more problematic. So one of the things that we want to try to do with our experiments here is to just start with a range of possibilities, initiating factors, and that includes varying CO2 to various levels, and then seeing what the model produces as an outcome. And so, again, this is after about 450 years, but this run has now gone 700 years, and this position of the sea ice front at roughly 30 degrees latitude, north and south, really hasn't changed much over time. So that's now more or less stable. It's interesting to us because that leaves this huge swath of tropical ocean still open, and I don't have sea surface temperature plots to show you, but there's a very narrow band right along the equator that stays as warm as 12 degrees C. And so it's suggesting to us that Model E is not going to get into a condition where the sea ice cover will become total. And it's encouraging to us because of all the modeling efforts that have been done, the only efforts that have trouble getting the total sea ice cover are the coupled ocean atmosphere models, which should not be surprising because it's got the fuller dynamic response and all the feedbacks associated, and here we are coming up with similar results. So it's kind of neat because it suggests to us that even at a point in Earth history that was incredibly cold from our perspective, there's still plenty of room for there to be habitable environments for the life that existed at that time.
I think next is going to be Nancy. She's going to talk about
Okay, thanks, Mike. Okay. I'm not going to be as scholarly as Linda because these are kind of results hot off the press. And sorry, Mike, I didn't do all the kind of background. But, so Mike put in this slide from a Physics Today article. But so I'm interested in Mstars or red dwarf stars just because their spectrum is so different from our sun, and I research on photosynthesis, which is very adaptive to the stellar spectrum. So I'm just interested to see how photosynthesis might adapt differently to planets orbiting red dwarf stars. So the cool things about red dwarf stars is that they're really cool and long-lived. So with hundreds of billion years, life has lots of time to evolve and get established. So they are candidates for having life. There's some interesting things about them. When they're really young, they emit big UV flares, so life might have trouble getting started. But then when they're, they get protected underwater. And then when they're mature, the stars hardly emit any UV. So you actually don't need, maybe you don't even need an ozone layer to protect yourself on Earth. They emit very low visible light compared to our sun and much higher near infrared light. So for me, for photosynthesis, it's interesting because there is photosynthesis that operates in the near infrared, and it's not oxygenic photosynthesis. But there's questions about how these things might adapt under different stellar conditions. So a planet that's in the habitable zone around a dwarf star is probably going to be really close. It's going to be close in like about 0.1 AU or so. So it could get tidally locked, but we won't deal with that yet. People have investigated what happens to climates of a planet that's tidally locked. And we might do that with this GCM too. What else? Is there anything I should say about this clock?
Well,
they're the most abundant type of star in our galaxy too. And not only that, because they're dimmer and the planets are close, and it's easier to find planets around them. Because with a transit doesn't take forever, because usually you need about 3 transits before you decide there really is something there.
Well, it's also because the stellar disk is so tiny.
Yeah.
I mean, they're not much bigger than Jupiter.
Yeah.
The really low mass ones, so the percentage of the stellar disk occulted by the planet is proportionally that much.
Yeah. Okay. So they're of interest because they're really different and they're also easier. So that background. So just some idea of what the stellar spectrum look like. On the top, I have the equivalent top of the atmosphere incident radiation for planet with inhabitable, about the same flux. It's reasonably same solar constant that the Earth gets for the Earth and the Sun, and then for F star, K star, and a few different Mstars of different temperatures. The bottom is actually what I'm interested in is the photon flux rather than the energy flux, because photosynthesis is a quantum process. You see the spectral shape is quite different, and photosynthesis will be adapted to these kind of quantities rather than this energy flux. But I won't be showing that. And underwater, you can see how water absorbs radiation, absorbed heavily in the infrared. So some interesting about that is, could photosynthesis start that deep down if it's not getting, could you get near-infrared photosynthesis that deep down? Probably couldn't. Anyway, you get pigments adapted to different spectral qualities of light in the ocean.
Can I ask a sort of tangential, stupid question?
Yeah.
I think I've read somewhere that there's some evidence that organisms around hydrothermal vents
Yeah.
actually exploiting the ion photons.
Chemosynthesis.
Yeah.
What about, I mean, there are plenty of living organisms that don't need
Well,
photosynthesis.
actually, I meant that there
Like
was-
at the hydrothermal
Okay,
Right.
so there's that. The
That's not what I
hydrothermal
said.
vents are interesting for two things. They are ecosystems that are independent of photosynthesis around hydrothermal vents because they're living off of methane. But there's also, type of cyanobacteria. It's not oxygenic photosynthesis, but it has been found by somebody diving in the Albedo and retrieving sample and culturing it, living off of the light, off of hydrothermal vent, and it's getting about the same amount of light as a red algae that was discovered living like 80 meters down in the Black Sea. So about the same amount of light the photosynthesis can survive. So you could have photosynthesis on another planet deep in the ocean that we couldn't see with a telescope. All right.
No, but what I was suggesting is that you could have life that's independent of photosynthesis.
Oh right, yeah. So if you have like Mars might have methane and you'll have life, right?
But that's a fact, it's not a suggestion. I mean, people
I mean,
found
you know
it
that.
down deeper 1 kilometer, a big restaurant.
Right.
Everybody's
Right.
feeding off sulfur dioxide and
Yeah,
acid sulfuric acid.
Yeah.
And it's dark as hell.
Like,
So
yeah.
life
Yeah.
and photosynthesis
The-
are just a very ancient kind of concept.
The thing
It's
about
perfectly-
photosynthesis,
That's okay.
is that the starlight is this ubiquitous energy source, and it can drive a kind of a redox cycle on the planet that you don't get with hydrothermal vents, which are going to, I don't know which last one, star or hydrothermal vents. I think the star last one. I don't know.
Star will probably last.
Star will
I mean,
so-
one of these low mass stars
yeah.
can have a trillion-year
Yeah.
hydrogen burning lifetime, which
Yeah.
geophysics is probably going to be over
Right,
long
right.
before then. But I mean,
Right.
it's true that the
Yeah.
majority of life on Earth is
Yeah.
not photosynthetic.
Exactly.
It doesn't give a damn about light.
Exactly.
Right? It lives in the subsurface.
Yeah.
But it's very slow metabolism, and it may be that it's very hard to spot from afar because it's not putting a big fingerprint on the atmospheric chemistry or on the surface chemistry.
Yeah, the earliest life on Earth may or may not have been photosynthetic. So it's chemoautotropic.
Probably not, because oxygen is a secondary gas.
Well,
so to
there's
speak.
anoxygenic. The earliest photosynthesis was not oxygenic also.
But cyanobacteria 4.5 billion years ago in Australia.
Four point
No,
four,
no, no,
and then at that
Stromatolite,
3.5
stromatolite.
billion maybe.
3.8 billion years.
3.8.
At
Okay,
earliest.
I'm overdoing it.
Yeah.
But anyway, 3.8, big difference.
Yeah,
3.8.
anyway, yes, there's other life besides photosynthesis. I just happen to be, that was my area, so that's why I'm interested. Okay, you can ask other people. You can ask Sean Donegal-Goldman about sulfur metabolisms too. So here's comparison between our sun stellar spectrum and an Mstar that I got from Aki Roverge down at Goddard Space Flight Center. So on the left is the sun from Judith Lean, and that's what's in our GCM. And the right is GJ876, which is an Mstar. Let's see. Middle plot I just expanded the short wave a little bit more to see it better. Bottom is how these spectra are represented in the GCM. These are the fractions of total stellar flux. They're not flux, they're fractions of total flux. So on the left, Andy Lacey's picked out these bands, he eyeballed them, and some of them are 8-meter charter bands, and they're really messy. That's how it's broken down. In the right, using those same bands, that's how the fractions break down for the Mstar. So stack these into the GCM, and so some of the things interesting about the Mstar, because it's shifted out to the near infrared, more less visible. So how the energy balance with different surfaces will work differently, especially with water and snow and ice. So here are a bunch of let's see, spectral albedos for water, snow, and ice. The nice, more finely defined plot is by Albedo Shields, who did do an Mstar simulation with these different kinds of albedos, getting a range between ocean, really dark, to snow, very bright, and some mixtures between ice that has no bubbles to snow that has lots of bubbles.
For an Mstar.
What?
This is for an Mstar.
Yeah, she did an Mstar simulation. Down below is the water's absorption coefficient, spectral absorption coefficient. You can see it goes up in the near infrared and the infrared. And just for comparison, on the right is how GISS represents the albedos of snow and ice, including old snow, land ice, snow over ice, etc. We do have algorithms that Igor knows about that check how old the snow is, and that alters. And you can see melt pond albedo is really low. Old snow is dimmer than new snow. So what did we get? So we did a model-y run. I put this, and Mike graciously took over and stuck in a few folks run because I neglected to do that first time. So we did AR 5-minute run using pre-industrial stellar constant and preflux run, and using the GJ876 stellar spectrum. What we got? Well, on the top, the surface temperature is the sun, and then below that GJ876, and below GJ876 minus the sun, you can see the Mstar gets a lot warmer. The Earth gets a lot warmer under the Mstar. And also, interesting is precip goes down by like a third. And that's odd, or not.
These are very preliminary. We just did these
yeah, these are
yesterday.
preliminary. Yeah.
So we're not even sure what it means yet.
Yeah. yeah. So I just whipped these out yesterday.
Can I ask a question? You said the Mstar is dimmer, so it's not emitting as much
right, so
radiation. So why is the Earth, when you simulate it with the Mstar, why is it getting warmer?
We put the planet closer to the Mstar, so it's getting the same amount of radiation total.
Oh, I see.
It's getting the same solar constant as the Earth, but it's just got a different spectrum.
Oh, because of that shift in the spectral properties,
Yeah.
that's making the Earth warmer?
Yep.
Is that what you're saying?
Yep.
Okay.
Yeah. So part of it could be because surface albedos of ice. That was what OMA Shields hypothesized in their paper and showed a lot of that. But there's interesting. You look at the planetary albedo. Top sun, middle is GA76. You can see, the albedo over the ice-covered area goes down a lot. And I think that Igor suggested, and it looks like it's true. I have another plot that show ice depth, and it's probably because the planet's warmer, it's snowing less, and the ice is getting old. There's less snow, and so its albedo is going down because it's getting snow. Those are prescribed ice areas.
I wouldn't focus so much on the ice albedo.
What?
The ice is not a huge fraction of the world. I mean, you can see in the plot that it changed over the oceans as well.
Yeah. No, it changed over any ice, snow, and ocean too. So, yeah. I mean, yes.
Actually similar, but like over the continents,
Yeah.
also the albedo decrease.
Yeah, I guess the albedo kind of went down overall. It's interesting. So anyway, we're still trying to tease out the different reasons. Yeah.
So did you get rid of ozone and change the stratosphere?
We didn't do interactive chemistry. This is the mint run.
But you said there's no UV, or there's little UV.
There's low
In the
UV.
spectrum.
So I don't know what the chemistry is doing with the mint run.
Oh, I don't know.
Okay.
We start with
Yeah.
present 1850 amounts from
Yeah.
all those gases, and
Yeah.
then evolve in time.
Yeah, we haven't changed the atmospheric composition.
But you're right, there's less
Yeah.
UV, and
It will
probably
change.
affect the ozone concentration over time.
Are there clouds in here?
Next plot. Let's do the right-hand side, and then we'll look at the clouds on the next plot. This is on the right-hand side is the shortwave heating rate by latitude versus height. And you can see because of the shift to the near infrared, there's a lot more absorbance up in the atmosphere before it gets down to the surface. Tony thinks that's why the precip level so is declining a lot, because it's not getting down to the surface and the upper atmosphere is heating up. Okay, total cloud coverage on the right hand side. So I guess it goes up in some places and down other places.
So can you go back one? What was the head of the vertical axis on that? It's just hard to read. That's from 0 to 1 atmosphere. I got you. This wasn't sure what the scale is.
So that's just water vapor absorbing the incoming IR, is that?
I think so. Yeah. Or same scale.
But this planetary the planetary albedo, does it include the clouds?
The planetary albedo includes everything.
Yeah, so if the clouds are changing a lot.
Yeah, so clouds went up, but albedo went down. So clouds went up in some places and down in other places, but the albedo overall kind of went down. I should put them next to each other. Anyway, so that tease out the different. There's no depth on the left hand side. You can see it way down. But I don't know, the North Pole, why did it go up? Is that some kind of weird thing in the model?
Well, the atmosphere is warmer and can transport more moisture to higher latitudes, so the snowfall rate may increase.
Okay, but how come the Antarctic went down? Okay.
Again, we don't have enough answers to
I think that's all I
Yeah, I think that's it.
today, yeah, okay.
Okay, great.
Thank you.
Thank you so much. Okay, so the other thing we worked on was, as I say here, getting from Earth to Mars. And I'll just go through the steps that we took roughly to get to what we think is close to modern day Mars. We're missing some elements that we'll show you later on. The first thing we did was mess around with the gravity and radius to get Mars to be the right size and the right gravity. And that took some time. We found some problems in the model. It didn't like certain things about the gravity we were using and things like that. I'm not going to go into those details. It would take too long. But we did manage to get that. It was one of the first things we got straightened out. Then we started playing around with using Martian insolation, 0.43 of Earth insolation. And thanks to Max, he expanded the radiation bound of the model so that we can go to colder temperatures, because the model doesn't like, what is it? Was it, the bound was, what was it before Max? It was 126K, I think, was the lower bound on the model. 124K, yeah. So he did some extrapolations that Gary Russell and Andy did a couple years ago. He just basically followed the same prescription, and now the model can go anywhere between 0 and 400 based on the radiation side. So that made that possible. And Max did some other, what he calls engineering. I wish he talked more about the engineering, but he said it's just engineering he did. He basically got our first Mars model with a desert world, no oceans, and he got topography from Jeff Jonas to put into the model, and got that aspect of the model working in a sense. Changed the atmospheric pressure and some of the constituents. It's mostly CO2 with trace water and no ozone, as far as the radiation is concerned. And then a large amount of effort was spent trying to get the orbital parameters right for Mars, because this model has a lot of hard-coded parameters into it for Earth, radius, rotation, et cetera, and Tom Clooney, thank goodness, got involved with this, and after some intense consultations with Michael Allison, he actually got it working. So there was a lot of debate amongst us about how to handle the calendar. Most people use a solar longitude to describe where Mars is in its orbit, but this being an Earth-centric place, and us being interested in education, that'll be another big part of the NAI. We decided, and probably some of you are going to flip out when I tell you, we decided to use a kind of an Earth calendar, in a sense. So we have 12 months for the Martian calendar, and those 12 months have variable lengths in each month, but they can be as long as 60 days, those months, to get that to work right. So that when we talk about Mars in January, well, we know is that Mars in January is winter in the northern hemisphere of Mars, just like it is on Earth. And we talk about June, we talk about summer in the northern hemisphere of Mars. So we can get that analogy so that when in the future people play with this model, they'll understand what those things are quite intuitive without trying to figure out what the solar. We can get the solar longitude out very easily from the model. That's the last thing that Tom is cleaning up now, so that is output as well as a diagnostic. But at least we have this kind of very quick way to do diagnostics, as everybody here does all the time. You know, they do June, July, August diagnostics for 10 years, or December, January, February diagnostics. So of course, Mars, you don't need all 3 months because it doesn't have oceans, so it equilibrates pretty quickly. So more or less you just need June and December. At least that's what we've seen so far.
But is it 12 or 9? Is it actually same?
It's 660 days. I forget the exact length, but divided into 12 months, a variable length each month. Yeah.
So what's the how do you call it, inclination?
Inclination
of
of Mars is very similar to Earth's. We haven't changed that so far, but that's a trivial change. That's easy. That's already allowed. Gary put this in 30 years ago into the model.
And can you also change it within a run, because Mars doesn't have the moon to.
It doesn't change that fast. It's not a concern.
Okay.
At this stage.
Alright.
But we'll talk about that in a minute.
Okay.
It doesn't change on those kind of timescales that we're worried about, at least for this particular model. And then there's going to be some future work on clouds, and Andy has 2 slides he's going to show us about how he's going to handle the cloud scheme, because right now we don't have any clouds in the model as it stands. And then Igor's going to talk about his CO2 condensation scheme in some more slides. And just before we get there, I'll also mention that Kostas is working on the photolysis of the code, and he told me he couldn't make it today because he's down at Goddard actually talking to them how he's going to modify the chemistry in the model to handle Mars. He said he was able to decouple the photolysis code from the current chemistry scheme, and it compiles with the current chemistry absent, which is good, he says, because then he can make the photolysis code work with any chemistry he wants. And his belief, after removing some more hard-coded stuff in the model, that it's probably easier just to replace the chemistry code in the model completely for a given planet than to try to make the one that's in there right now work with future stuff, because there's so much hard-coded stuff. So that's what Kostas has told us, and again, that's coming down in the next year or so. Another very important thing is to get collisionally induced absorption for CO2 working. Now, that's especially the case for paleo Mars. And eventually, long down the road, will be to ability to increase or decrease land ice, polar ice caps. It's very important for Mars. That's something I haven't studied as a master's student 20 years ago, 25 years ago, I should say, from Viking orbiter data, where we could see the caps moving quite a lot, and that's a long discussion we can talk about. So Andy, why don't you talk about these
What do you do with dust?
Getting there. Dust that's Jeff Jonas's responsibility, and that's coming down the road as well.
A pretty good question. Why didn't you just turn on water clouds?
Yeah, good question. Why?
Because we put so little water vapor.
Yeah, there's a little water vapor in
into
there.
the atmosphere and the soil.
There's just no supersaturation with respect to ice anyway.
There could be, but they would be very, very thin.
So there you go.
All right, so all I've done is some background load calculations, really, putting together for this proposal. Basically, I read in the French group has really, it was a French GCM group has really done a lot, and a good bit with clouds, as has the Ames group. But I found the French group's publications a little more revealing. At any rate, so there was mention of particles falling very, very fast, and if cloud droplets are falling very, very fast, that's a big numerical problem. It's something we have to deal with. Anyway, so let me back up. So there are going to be 2 condensing species. There's CO2, and that should be very high in the atmosphere, the stratosphere, except for the water. The poles in the winter. So there will be CO2 condensing there. And the water ice will be at much lower altitudes, and everyone is ignoring interactions. I think we're going to ignore interactions between those 2, because no one has any idea how those would interact anyways. The other thing I noticed is that no one treats, I think no one knows how the abundance of these by number is totally unknown. We don't know. I mean, you can assume that if all the water clouds are forming on dust, and you can make some intelligent guesses about how many dust particles there are, I suppose. But at any rate, so these are all ice particles, and aggregation of ice is not understood very well on Earth. We think it happens a lot when you get close to the melting temperature. Dendrites will tangle, but other than that, we don't think ice aggregates very effectively. So everyone is ignoring ice aggregation. So that makes it much simpler, in which we have, for each condensing species, we only have to consider 3 processes: nucleation, so creating a new cloud particle; deposition and sublimation, so diffusional growth and evaporation; and then sedimentation. So basically, this is all my back of envelope calculations are about the sedimentation, which is right now I am coding up, or I have been, and I've taken a little break, and I'm going to get back to it. This 2-moment microphysics, the Morrison-Gelman microphysics from the MCAR scheme. And 2 moments mean we're predicting prognostic variables for the 0th moment, which is the number concentration, and the 3rd moment, which is the mass concentration. Right now, the model only predicts mass concentrations. And it also allows for mixed phase, but that's not, we're not going to worry about any liquid phase here. So the current version that I was and will be, well, perhaps implementing again of that code treats fast falling things. So basically so consider water. There's cloud droplets which fall, but fall slowly, and then there's rain which falls quickly. And it falls so fast that you would go through several layers in one half-hour time step. So this is diagnostic treatment. So it's not a prognostic variable, it's a diagnostic variable. There's no memory of it. That causes problems when you're trying to do indirect effects, as Andrew Gelman spoke about when he was here a few months ago. So they have, I know their manuscript is out and being reviewed, a new treatment which is prognostic treatment of rains to get around this problem of indirect effects. So there's a memory, the rain sticks around. And so just by substepping, you just take a whole bunch of substeps for the microphysics, which slow the model down a little bit. And so basically, I was just curious as to whether we're going to get away with, whether I can justify waiting for them to release the new treatment until I code it up, or whether I should just go forward with the old treatment, which is the diagnostic treatment of rain. So basically my question is, how fast are these particles going to fall? So these are extremely back of envelope calculations. So the top one is fall speed in meters per second, then Reynolds number for the sedimentation, then the Knudsen number, which is the mean free path of the atmosphere divided by the size of the particle. And so this is, I didn't mean this one to go first. Can we do the other one first? So this is something like what I eyeball as the surface. So 200 Kelvin and 6 millibars for the modern surface of Mars. Maybe that's not when the atmosphere is condensed out, so maybe that's the summer. I don't know. So basically, this is just, you assume the simplest possible expression for fall speeds, which is Stokes flow. It's just viscous flow, and it's just there's no turbulence basically. And so it's a very simple expression, which is basically they fall, the higher G is, the faster they fall. This should really be delta, the difference in the densities between the atmosphere and particles. But the particles always have such a higher density than the atmosphere, you throw away the atmospheric density. Then there's the square of the size of the particle and the viscosity in the denominator. So there's this kinetic factor, which is the fact that the air is not a continuum when it gets very rarefied, and so there's gas kinetic effects. And so here's this gas kinetic effect, which depends on the ratio of the mean free path to the diameter. So this is near the surface, and basically for very small particles, yeah, you get a big kinetic effect. But for the most part, the kinetic effects are small, so this is the fall speed with kinetic effects and without. So you're only getting up to a meter per second for pretty good size, what I would consider cloud particle, where there's no aggregation making big things. I'm not even sure how big these things are going to get, but that's 100 microns. So a meter per second, if you take a half-hour time step, that goes about 1.8 kilometers. So I don't know what our vertical resolution is, but I would think that would be safe. And just to check, is it okay to use even this simplified expression? The Reynolds number, it's borderline. I would like to have seen it much less than 1, but anyway, it's easy enough to correct that. So now for the other one. So now here's my totally, really made up a little bit of what I think the upper atmosphere is. So 100th of the surface pressure, so 6 pascals rather than 600 pascals, and 100K colder. And at this point, now you are kind of getting, so you have these huge kinetic effects because the atmosphere is so thin. And fortunately, Reynolds numbers are still small, so you can still use this simple expression. But we're really getting, we're getting up to many meters per second, such that we would need 5 or 10 kilometer thick clouds. Grid cells. So. I take home from this, I will wait for the next version of the 2-moment scheme that has sub-stepped precipitation, so I'll not be working on the Mars clouds for a little while.
That's the take-home message. You found a way out of the world. Okay,
And when we were working on many years ago on the solar nebula, the condensation of the solar nebula, we find out that precisely because the Reynolds number is so small, particles are very sticky. So your assumption they are not sticky, I don't think it's.
What kind of particles?
Well, it was at that time which is ice, and precisely because they move so slowly, the stickiness becomes very important. So to treat them as they don't stick. If that were the case, then I don't think you would be able to find a planetary system around the sun. That was precisely the stickiness of the particles that make them go together, and then when they got a certain mass, then gravity took over and they become bigger and bigger. But at the phase t equals 0, as it were, that was the stickiness of the particles that put them together. Precisely because they fall so slowly. In our case, because they move so slowly.
Because they move slowly, they're sticky?
Well, if the other way around, if the Reynolds number were very light, were very turbulent, they would never be able to stick to one another because they're being reshaped all the time by turbulence. But since this is a laminar flow, because this Reynolds number is 0 for practical purposes, then to say that those stick, I think it goes against the very definition of your Reynolds number.
I don't know about it going against the definition, but that's an interesting point. We can talk about that later.
Yeah, but that's
anyway. Then it just adds a whole bunch more complexity of things we don't know.
Well, but this is not a complexity. This is
the
the real assumption that I think is at fault here. I mean, and there is I can dig up the paper when this guy did all the stickiness problem, and they changed very considerably the picture that we have of the solar nebula, because we were not able to. The practical problem was that nobody was able to get these particles to stick together. I mean, I didn't. And so you learn from the solar system, and you have to form it in a very question of 10, 20 million years, because that's what the data show. You take a star after 10 million years, there is no dust. So somehow, rather, that dust did get into bigger objects, and those bigger objects started off with this stickiness, which gives rise to bigger problems, bigger sizes, until, as I said, gravity took over and they made them collapse. So I think it's
well, rates of sticking over millions of years is different than rates of
No, I'm saying.
Okay, guys, we'll talk about this later because we're up, and I want you to just talk about a CO2 condensation, and you guys can.
Well, that's a scientific issue. I mean,
afterward, we talk about it because everybody wants to probably leave. It's 2 o'clock. If you want to leave, you can. But otherwise, I want Igor to talk a little bit about his CO2 condensation.
I want to say one more thing, which is the fact that CO2 is going to be condensing out in the atmosphere is something I talked to Tony, it's like it's not obvious for us how to deal with that, but the fact that Igor has started to condense out the atmosphere at the surface maybe will pave the way for that.
Let's hope so. So this is just a simulation run, 10-year average for December for Mars with the right amount of CO2, at least as far as the radiation model sees at 6 millibar atmosphere. You can see it's quite cold. Max here is only -12, whereas the real Mars is as high as 35. So we're still a few degrees off. But I want Igor to talk about the CO2 stuff he got and how it compares to reality. So you decide which picture you want to show first.
Yes.
No.
So that what you showed basically is without CO2 condensation.
Yes, this is what that.
Yeah. So I guess I already understood that on Mars basically it is so cold, and first of all, atmosphere is nearly completely CO2, and it's so cold that sometimes you condense
certain amount of CO2. And actually it's up to 30% of the atmosphere that can be condensed during the season. So it's non-trivial thing, and this is something that we never observe on Earth. So this is completely like special for Mars or other planets.
And so what's the concentration of CO2 in the atmosphere about?
What's concentration?
Yeah, what's the concentration of CO2?
95%.
On Mars,
almost 100%.
95%.
Okay.
So we assume that it's 100%.
Okay, wow.
Yeah, so yeah.
So wait, do we get like opacity from CO2 then? Model? Does it we get
It's in the
You
radiation
can
scheme.
shelter
we get the
It's in the radiation scheme.
Yeah, but it's only 6 millibars anyway. It's very thin atmosphere.
Okay.
So, but anyway, yeah, it can condense and change the amount of atmospheric mass and change the pressure and yeah. Well, first of all, I want to say that what we are doing is not something terribly complicated and or new. It was done in many models, and Michael Ellison already did it here at GISS like many years ago with in his previous in basically in the model version of GCM which was used at that time. So well, anyway, so the mechanism is completely different actually from what we see on Earth with respect to water, because first of all, with water we can neglect the change of the mass of the atmosphere, and that's what we do on Earth when we condense water. But with water there is also some complication, because well, since you don't have that much water when you condense it somewhere, it is you usually have a limiting factor of how much water basically is diffused to the areas where condensed due to basically turbulent transfer of water particles. But here in pure CO2 atmosphere, the task is easier because you have all the CO2 you need to condense if you want to condense it. So the approach here is basically we don't condense anything in the bulk of the atmosphere, but we just condense everything at the surface. So it's basically just CO2 frost what we do. And since pretty much we have enough CO2 to do this, so the condensation is computed from the point of view of energy balance. So basically what we say that well, if surface becomes too cold, then we should start condensing CO2, and CO2 condensate cannot go below the temperature of condensation. So pretty much if surface tries to get colder, that means that we should just condense a little more of CO2, and latent heat will balance that heat that we are missing. So that's pretty much what I'm doing in land surface model. I'm just computing the amount of latent heat which is missing which is necessary to keep the surface at the condensation temperature or above, and this condensate then is subtracted from the atmosphere. So those pictures which we see, yeah, so those are just 4 seasons. That's according to our calendar, it's Mars, June, September, and December. And so in March we have the highest condensation in northern hemisphere, and in September it's basically like the maximum condensation in the southern hemisphere. But this is just the amount of condensate, so like the numbers are, as you can see much, but it's like this scale is up to 800 kilograms per meter square. So it's a lot. So if you think that you have to condense a third of the atmosphere over a pretty small area, actually, over the polar area, then fluxes are very high. So one has to take this into account. And those are temperatures. That's, well, yes, you see what you are expecting to see. And
What's the temperature the CO2 condensed?
Huh?
What is the temperature the CO2 starts
here is around minus 130 Celsius.
We cannot
but
read
it-
anything.
But it actually changes in a different. Yeah, well, sorry. But actually it
Zero.
changes.
What's the condensation temperature of CO2 is what she's asking.
Yeah.
It's around 145 Kelvin, I think.
That's what she
Yeah.
wants.
Yeah, but it changes with respect to pressure, so that makes the problem a little more difficult because basically you have to solve the equation when you condense. You have to solve the equation with respect to pressure because you are changing the pressure at the same time. And but yeah, it's around the temperature. So basically here surface temperature never falls down than lower than 130 degrees Celsius for condensation.
Let's go from minus 130 to minus 18, it looks like. That's the scale.
The scale is from minus 130 to minus 10.
Minus 10. Oh,
Yes.
okay. I can't even read it on this screen.
Yeah.
Go back. That's the
Yeah.
wrong one.
Do you want to show?
No, you're going to show you show your slides. Go back. Go back.
Do you want to talk about
No,
this
I
slide
don't.
first?
Go back to your slides. You
No,
have-
well, I'm saying if you're not going to talk about it,
Oh, you want to talk about it?
I just wanted to show because that's the difference between.
Didn't even know you were slides were in here.
Mike,
Okay, well, if you want to talk about it, then I guess I can.
No, I won't. You can talk about it.
Yeah, well, I guess that shows the difference between around this and without condensation. So you can see that basically, yes, in 2 seasons, nothing changes too much in the mid latitudes, but close to the poles, you definitely see considerable change in temperature because condensation doesn't allow temperature to go below condensation point.
What do you mean T-surf equals 0.96?
That's the mean for the whole planet. That's all. It's the difference. between the
0.96
two.
what?
Celsius. Sorry. It's increased by 0.96 Celsius
Oh, it's a
between.
delta.
Yes, it's a delta.
Anyway, so this is just shows how pressure changes. Those are months. Those are seasonal cycles in pressure. Well, it's not 30%, I guess, as people claim, but I'll show in another slide. It still looks like we are doing good. So and seasonal cycle is uneven, so we condense more on southern pole than on north pole, and these are amounts of CO2 condensate. So blue is on southern pole and green is on north pole. So you can see that actually they intersect. Basically, you don't run out of condensate on one pole when you already start to condense on another pole. So you always have some amount of CO2 condensed in our model. But I don't know if it happens in the real world, but probably the same thing. Yeah, and this is just what I wanted to show. I didn't expect actually much, but what I did, I tried to put just the dump pressure from the cell, which is close to landing point of Viking 2 satellite, which was measuring different stuff on Mars. Those are measurements from Viking 2, red line. It's a seasonal cycle of pressure, and that's what we are getting now in the model. So I would say it's pretty close.
Igor also generated this yesterday.
Yeah.
Why do you think of the surface pressure as 6 millibars, which is, I thought, the triple point or something?
Well, these are different. These are not at that data. They're at different
So the
altitudes.
6 millibars is just it's sea level or whatever average.
It's more or less averaged. I didn't quite actually understand it. Do they really have that data? I mean, do they really know exactly what the average over this?
That used to be 6 millibars. Used to be the definition of 0 altitude, but I
Yeah.
think more recently there's such a detailed map of altimetry that there's an actual better average that can calculate. But I can't tell you what it is.
Yeah.
There are 3 digits of accuracy on Wikipedia
On the what?
On the pressure.
for the mean surface.
So this is at a lower elevation.
Yeah.
Yeah, but anyway, yes, this is just particular points.
I got it.
Yeah,
It's good.
That's
yeah.
amazing.
Yeah, and also I
It's
have
probably all wrong, but it was good.
I also have chosen this satellite because it was on a flat area, so we could use its coarse resolution and still get something reasonable.
So you're still using Viking data? I mean, have there been subsequent missions on doing your data?
Yeah,
Recent missions?
just yesterday I was asked to try to do it
Curiosity.
for Curiosity, and it didn't look that good because Curiosity actually traveling between the mountains, so it's somewhere deep in the valley. But when you compute it on GCM cell, the cell is very big, so the average elevation is much higher. So what I'm getting actually is not quite relevant to what this landing. This rover is getting, because it is traveling much deeper in the valley.
What about the other rovers like Opportunity and Spirit and Pathfinder?
Well, we can look at them. As Mike mentioned, I did it just yesterday, and I didn't even expect to get.
Viking had a dedicated meteorological package. I'm not sure that these other rovers have anything like that.
Well, they all have some basic.
They may have something very
Yeah.
basic.
Yeah.
Well, Curiosity is measuring pressure, yes. But yeah, well, the difference between what we computed and what Curiosity was measuring is at least 1 millibar. I think even more, like 1.5 millibars. And I think that's because it's actually somewhere deep in the valley.
The difference in elevation.
Yeah, we just don't resolve that.
This is the 4x5 model.
Yeah.
So it's not very high.
Yeah.
From your previous slide, it looked like you had done 8 continuous orbits. Is that correct?
What do you mean?
No, he's done a 30-year run.
Oh, really?
He's only showing part of the run.
I was just counting
Yeah,
the blips
well-
there, but
Well, I did many runs. So this is actually the start of 100 months. So I don't know, years, like 9 years. And I'm showing it from the very beginning, so you can see that we start from no condensation atmosphere. So the first like half a year there is no condensation, and then like we condense it on southern pole, then on north pole, and then basically after the first year it already gets to equilibrium. So
but that looks like mass is very well conserved over the course of the simulation.
well, it should be, yeah. Actually,
Yeah,
I
but that's been a problem with Mars GCMs in long-running simulations of the CO2 mass pressure balance.
well, the way we program it, it's supposed to conserve it. I mean, unless due to machine accuracy there is something. But actually, yeah, GISS GCM has an algorithm which actually conserves atmospheric mass just described, and you probably remember that what you actually have to modify it so that it would work with CO2 condensation. I just disabled it, so basically what we see is a real conservation of mass in the atmosphere, so we don't force it to be conserved. It's just land surface takes and puts back mass, and atmospheric dynamics, I guess, does what it wants to do, and we don't see any loss in the mass. Well, this over such should be it. So.
Okay. All right. So we have way more material than we can show. This was the only other thing I wanted to show quickly was Mars zonal mean temperature profile, comparing Mars Global Surveyor versus our model, and at least the profile looks similar to something Tony dug out of the data for the CO2 condensation run for latitude and pressure. So again, another sign that things are not too far off. Again, even though we don't have dust in the model and we don't have clouds, some things are working. It's not clear why they're working so well, but it's remarkable that they are. Probably for all the wrong reasons, like this. I'm not going to go into this because I've gone way over time, but long term is, of course, to get this right and then go on to paleo Mars. We talked about variable orbital parameters, and people have calculated the orbital parameters for Mars back for 1 billion years. I'm sure Caleb can tell us whether it's even feasible or rubbish or not. But anyway, it's been done. You can see the obliquities changing by large amounts on Mars because it doesn't have a moon, as was pointed out, etc. But that's all stuff that we're going to put into the model over the longer term, is to allow those kind of things, at least in that. And a lot of it's already possible. The mechanics are already there. add oceans. I already mentioned closely induced absorption, cloud possibilities, et cetera, et cetera. And I'm not going to go into this, but anyway. So I just give you a flavor of what we're working on and what the various groups inside this big collaboration are doing. And if you have more questions, please come and talk to us. You know who we all are now. Most of us are here. And if you want to join in and contribute and have some fun with these modified models, please let us know. We have them. They're not, a lot of the code's not committed yet, but we hope to merge all this stuff into the main repository so that we do not have a complete separate branch. The idea is that all this physics and changes will be put back into the main repository, and the way you run the model now will be exactly the same, but if you want to run these things, you just make some changes to the run deck parameters, and boom, you can run one of these other worlds. That's the goal we have for this project, so that we can leverage, unlike almost all of the institutes, the in-house expertise we have at GISS, which most of the planetary groups do in GCMs do not. Okay, so thanks a lot.
Mike, you started. Oh, sorry.
Yes.
Oh, since this was the theme of today's discussion was astrobiology.
Yes.
And we really haven't touched upon that at all. I would suggest that when you get into Paleo Mars, you want to go to a period in its ancient history when it may have been potentially habitable.
Well, that's
That's going to be done by the guys at Goddard.
The guys at Goddard.
The guys at Goddard on this team are very interested in that, and that's why I said in this previous slide, when you talk about add oceans, you know, a deeper atmosphere, et cetera, et cetera. That's all coming.
Yeah,
And the data from Curiosity is shedding a lot of light on that early period.
I mean, these guys down at Goddard are the Mars experts, so that's their bailiwick. That's their
okay,
business.
because I know a little bit about it also, so I mean I could have also
Okay, well, come
help
talk
you
to
out
us
on
then.
it.
That'd be fun.
Okay.
We're right now at the stage more of a comparative climatology.
I see. Yeah.
Yeah, we're at a very
They
preliminary
aim,
stage.
yeah, the long term, of course, habitability and then biology.
Yeah.
And I mean, of course, there's all these theories about where life first began in the solar system. Did it begin first on Mars? Maybe it first began on Venus. Venus had, if you look at the sun, Venus might have had liquid oceans or liquid water on the surface a couple billion years ago. But who knows? But those are all things we can explore over the longer term of this model. And I think we're one of the few groups in the world, assuming this takes off, that will be able to do that coherently. I think the other competition that we have are the French group.
Michael, but you started off saying, that's why I got lost up in that liquid water. No, liquid water, there's so much information here. What does one get out of this meeting here? As a non-expert in this field, what is the message that you're trying to get to us? Condensed. You started off saying there was liquid water with the signature of life. Fine. So why do we study the Earth? We know that life is here. So what is it, perhaps Linda will explain that, but why do we concentrate so much attention on Earth in which we have proof that there is life, intelligent or otherwise? I understand Mars in the past to study if there had an ocean before that. I would stand the Mstars because they may, if that. The second part of my question is, what is the relation between all this and those who are really these planetologists who are trying to find planets, and they find them every day in huge numbers?
Yeah.
So are you trying to help them out to tell them, look at Mstar preferentially? So why do we study Mstars?
No, I'm not saying that. What I'm saying is we want to, over the longer term, we want to give people a better idea of what candidate systems they should be looking at. I said in the very beginning.
That's what I said. So you want to tell observers what to observe?
Yeah.
Yes.
Okay.
That's the idea. Over the long term, that's what the goal would be. Look, these Mstars have planets in what we consider their habitable zone. We think they have these masses. Go and see what's in their atmospheres. I mean, we're not going to, these missions are, if they ever get launched, they're going to cost huge amounts of money. They're going to be scarce resources. I mean, Caleb can probably talk more about this.
No, I mean, the whole idea is that you're trying to find some from the theoretical point of view, and this is all collective knowledge, some suggestion for those who are going to observe, and hopefully find that you were right in your prediction that such and such planet may harbor life if it exists.
I mean, there's two goals. One is that. The other goal is the focus of the NAI is to study the solar system habitability through time, have some empirical data to test our models with, which we don't have for these other systems, right? So the idea is to interrogate our models with data that we actually
But
have.
there's no biology in your model. How can you possibly hope of answering that? The origin of life will remain forever an unsolved problem.
It's
By
still-
definition.
It's to emphasize the
Fortunately.
generality of the model. So the model right now is very specific to Earth. So we want to make it so it's more general on cases that we know something about.
Yeah, but why
And
do
so
we
we
still-
now have some confidence that we can push the model into other places, and then you can go off and explore and
So
more exotic
so
things.
what's also going to come out of this eventually, which we didn't get to talk about
Yeah.
today, is work that's going to be done mostly by people down at Goddard. And the general concept is, by looking at these various time slices in Earth history, Mars
Right.
history, Titan, Venus, what we will be able to generate ultimately is spectral characteristics of worlds that had a certain kind of general life. You know, early Earth is a non-oxygenated atmosphere with microbial life forms doing various things. So what we're going to hope to get out of the model are spectral signatures associated with different phases of habitability over time in the solar system. And then that ultimately will be fed through the models for the folks who are concerned about the spectral signatures of exoplanet systems and the potential for life. So they have some sense of, you know what, if you see this kind of spectra, this is a promising place to look, as opposed to this other place where we don't really know what this means. So
That's what I was looking for, that answer.
So that's ultimately where
That's the real key to the product. And it was not said, that's why I was in total state of.
but we're talking about what we're doing up here.
I
and
understand,
so
but that makes a lot of sense what you're saying. In the overall scheme of things, that's what you're trying to do, some signature that you give to the observers to look for such inside star, because that is the high probability of the slices of time, as you call it. That makes it. I don't understand why only Mstars and not any other.
We didn't say only M-stars, we just gave one example of using an
But there's
M-star.
so much effort on
to
M-star.
show-
How
So
about
It's not a lot of
Like-
effort, it's a week of work.
Like
It's not a lot of effort.
Oh, I see.
The
Oh,
point is,
wow.
there's a
If
proof
it's a
of
week of
concept.
work, then.
But the reason everybody gets focused on M stars and K stars, which
Right,
is
right,
a little
right.
bit bigger, is that in the nearby universe, our nearest neighbors are dominated by that type of star because they're the most numerous. And therefore, those are the stars that are close enough that when we have 30-meter size ground-based telescopes or next-generation space telescopes, those are the stars where we have some hope.
Okay, this
of
graph
making
here,
these observations.
this one, yes.
So
Local
so
neighborhood.
there are lots of nice G stars out there. They're too far
I-
away.
uh-huh.
That's the problem. So you've got to kind of look at your local neighborhood. And most of the local neighborhood are these low mass stars. So we're constrained by
The
that.
scale on the axis is what, the solar masses?
Stellar mass.
Stellar masses, in units of solar masses.
Yes.
Presumably. And the vertical is number of
Number
stars.
of stars.
I see, that's what you're referring to. you
Within
know.
30 light years.
Within
of
30
us.
light years.
Within the area, that we can read from here, yeah. So what you're referring to is the number of stars that goes up to 40, 60, is that the number?
60.
60. At 30 light years.
Yeah, right.
So that's you concentrate on because of that reason. I see. Now I understand what you say. I didn't understand the blue and the red when they were.
Blue is just a mass division, so points greater than 0.6 and less than 0.6 solar masses. That's kind of dividing.
Is that what the observers are already the observers concentrating on these M stars? Or now it's a random
Well, that's a
Well,
good question. So right now,
because what you see from the literature is that there is no discriminating. They just go look for some obscuration, right? That's
so
that's
it's
the technique.
right. So for example, the Kepler.
The
mission.
Kepler, yeah, the
So
classic.
it was looking at stars at like 1,000 light years
Exactly.
away, right? But that's because it was an efficient way to make a statistical survey of
Uh-huh.
the global population of planets.
And get people excited when they find something.
Yeah, and to
find a
know,
lot of
and to
planets.
know
Yeah.
roughly what the proportion of planets of different sizes is.
Right.
So one of the next things that will happen is this mission called TESS, which is an all-sky or almost all-sky.
Uh-huh.
So like Kepler, but it's scanning the whole sky, and
Right.
it's sensitive.
The US or Europe?
US. Yeah,
US.
MIT's the lead institution.
Uh-huh.
It's going to look at all of these guys and more. It's going to look, I forgot what the distance, effective distance is of its survey, but it's going to look at assume thousands, tens of thousands of low mass stars, but they're close to us.
Massive.
Transits again?
For transits, yeah. And so the trouble with transits is a pure chance if
Sure.
it happens transit. So you've got
Sure.
to look at, to see one, you've got to look at 200, roughly. So at a test, the expectation, because of what we now know from Kepler, is that there will be roughly 1,000 Earth-sized planets around these low-mass stars within, 50 light years of us. And those will be the first candidates, really, for follow-up, for looking at transmission spectroscopy and so on. So there's a lot of factors going into making
Yeah,
these
the
kind of
picture
choices.
is not clear at all. I mean, it seems to me that there's a disparity between the level of sophistication of this theoretical model, if you want to call it, and the state of the art in observing. I mean, it seems to be light years away.
They are very far away.
Completely far away. The observer is still shooting in the dark, and they found a lot of good planets, and they killed a lot of pigeons with the but here, is it just too early to do all this? I'm just being critical because I'm ignorant. That's all. But don't you think there is a little bit overkill? All this compared to the state of knowledge of what the observer can really use out of your output, and then be able to.
I mean, that's a good point. I think the thing is, even with JWST, right, there may be a couple of these stars that have a couple of planets transiting around them that JWST can look at with enough sensitivity to even ask whether there's CO2 or water vapor in the atmosphere of an Earth-sized planet. That's a big investment of time. So there will actually be a need to be able to say something, even in broad terms, about is there any hope in hell that planet has the temperate surface environment. It actually will matter because the investment of time for something like JWST or any of the 30-meter class ground-based telescopes, it's pretty.
Pretty heavy, yeah. I'm simply struck by the fact that we don't even know, as of now, we know everything about pulsars, everything about quasars, everything about anything, but we don't have a theory for the information of the solar system. Let's call a spade a spade. That's a fact. There's no theory. We don't know how the solar system got into being from the solar nebula. We don't. I worked for several years. I got frustrated, and I left.
Well, we knew
because there is no theory for it. So we don't even know how those planets.
There was a theory, but as we learned, it was fairly incomplete because now we find solar systems are completely different from our own, right? So it's worse than when you worked on it.
But I think,
Well, it could not be worse because we knew nothing. So if we had nothing, so
actually,
much worse than that.
I counter that by saying, well, there's a parallel there, because I think now we've been observing other planetary systems and protoplanetary systems in much greater detail. That in turn gives us a somewhat better idea of what may or may not have happened here, right? I mean, it's not finished. We don't have.
I understand.
And I think the same thing is true of this climate work, right? We've been trying to understand the Earth climate, a little bit about the solar system. Now we're seeing all these planets in an incredibly diverse array of configurations, they're going to have diverse chemistry, the majority of planets in our galaxy are these super Earths between the mass of Earth and Neptune. We don't have one of those in our solar system. We don't have the most representative type of planet in our solar system. So, interesting.
What is the closest mass of the Earth that has been found by Kepler?
One Earth mass.
Yes.
They did.
Except, it seems to have a huge hydrogen atmosphere. So it's one Earth mass. This is very recent. It's one Earth mass. It's 60% larger radius, and the only way that can be made to work is if you put in an atmosphere that's maybe hydrogen and helium on top of a small rocky planet. We had no idea things like that could exist.
And we started.
Would gravity be strong enough to hold the hydrogen and helium?
Well, if the
Wasn't strong enough for Earth.
If the planet is cool enough, maybe the planet is not. I mean, I think I forgot what the.
Yeah, but that's a relevant question. Yeah, the gravity of one solar mass may be not enough to keep the hydrogen.
Right. It may be a cool planet. I don't know what the stellar type is.
How far is that
maybe younger?
From the parent star? You don't know. Well, it's one mass. Actually, I didn't know that.
But yeah, so I mean, it's I mean,
getting close.
There's a few. Yeah, there's a few in that realm. So I think for me, I think the interesting thing about this work is, yes, it may seem overly complicated and ambitious, but you know, you're driven to ask new questions by this diversity of other planets that
No,
are
no,
gonna
I-
have to be
I
answered
just want to
by
learn,
models
that's all.
like this. Sorry.
That's good. No, thanks, Caleb.
Stop speech.
The director of the Astrobiology Institute.
Yeah, I have some knowledge.
Okay, you guys are please free to go, and if you want to